for watching this live session. So, welcome to everyone. Today's session is focused on the applications of computational fluid dynamics in the aeronautical and aerospace sector. This comprehensive overview will delve into how CFD, a branch of fluid mechanics that uses numerical analysis and data structures to solve and analyze the problems involving the fluid flows, is integral into the design and optimization of modern aircraft and spacecraft. As we explore this subject, we will examine the critical role that CFD enhancing the performance, safety, and environmental sustainability of aeronautical and aerospace systems. And computational fluid dynamics has become an indispensable tool in the aerospace industry, enabling the engineers and designers to simulate and study complex fluid flow behavior in an array of applications from the design of high performance aircraft wings to the thermal management system of spacecraft. The ability of a CFD to predict the behavior of fluid flow is whether gases or liquids around and within the engineered structures under a wide range of conditions is paramount. It allows for the modeling of aerodynamic, thermodynamic, and acoustic properties, which is crucial for the development of efficient and effective aerospace solutions. These simulations is help to reduce the need for expensive and time-consuming physical prototypes and speed up the development process and allow for the exploration of more innovative and daring aerospace designs. During this session, we will highlight the several specific applications of CFD in the aerospace sector, including its use in improving the aerodynamic performance of aircraft and enhancing the fuel efficiency of engines and designing the critical systems of spacecraft such as life support and heat shields. We will also discuss the future of CFD technology, including the integration of machine learning and artificial intelligence to create more accurate and efficient simulation models. The insights gained from the CFD simulations are not only pivotal for advancing the current aerospace technologies but also open doors to revolutionary designs and concepts that could shape the future of human and robotic space exploration. So, before we start Dr. Prem Kumar's session, I would like to give some start introduction about him. So we are privileged to have Dr. Prem Kumar PS as our guest speaker today, a distinguished academic and research professional in the field of aeronautical engineering. And currently, he holds the position of Associate Professor at the Department of Aeronautical Engineering at Kumar College of Technology in Coimbatore, India. And Dr. Prem Kumar embarked on his academic journey with a Bachelor of Engineering in Aeronautical Engineering from Park College of Engineering and Technology, affiliated with Bharatiyar University in Coimbatore. And his quest for knowledge is continued as he earned an MS by research in aerospace engineering and a PhD in the area of propeller aerodynamics from Madras Institute of Technology, Anna University, Chennai. And Dr. Prem Kumar is an expert in experimental and computational aerodynamics and has been actively involved in various government-funded research projects also. And his work includes the performance analysis of settling the chambers for sonic wind tunnels, experimental and computational studies on propeller characteristics and ice acceleration prediction over UAV wings. And his current research endeavors are focused on a DRDO funded project he aimed at enhancing micro propulsion system for unmanned aerial vehicles and underscoring his ongoing commitment to advancing cutting edge aerospace technology. And beyond his academic and research roles, Dr. Prem Kumar is also contributes significantly to the aerospace engineering community through the leadership and professional engagements. He serves as a journal reviewer for several prestigious international journals and holds key position in various professional societies such as the Aeronautical Society of India and the Indian Society for the Advancement of Materials and Process Engineering. His international experience includes working in the core engineering group at Bombardier Aerospace in Montreal, Canada. And Dr. Prem Kumar's scholarly contributions are extensive with over 50 international journal and conference publications. His achievements and dedication to the field have been recognized through the multiple awards and accolades, including the KCG Achievers Award and travel grants for the presenting his research internationally. And his presence today promises an insightful exploration technology in aerospace engineering. At the end, I would like to introduce to the motto of Dr. Prem Kumar, it's advancing aerospace through innovation and education. So I would like to hand over this session to Dr. Prem Kumar, and also thanks a lot for joining us today, and over to you, sir.
Thank you, Ms. Gandhi, for that detailed introduction. Also, I thank the Thames Tech and the Mastering Up for the invitation. So, hope my slide is visible.
Yeah,
Yes,
sir.
please. So, like Mr. Kunti mentioned, this is on the application of computational fluid dynamics, that is CFD, we say. In aeronautical and aerospace sector is my today's session topic. Glad I like to know about several registration all over the India from science and engineering background. So that I just made this presentation. Basically, what is CFD? So that what CFD generally does, because CFD is a known word all over the technically. So this is my flow. I planned for this today's presentation to brief about the introduction thing and CFD process outline, what generally CFD does. So how it influences the engineering area. Also some of the case studies, because the application you need to know where it gets into, right? So that is the main thing I'm planning. So before we start introduction, some years back I attended one of the session at Chennai. So I saw a video which is very impressive to know about day-to-day activities, how fluids are important in our life. So maybe just we'll start with that video, just go through, then we'll get into the technical content, please. that video, you might have observed the activities, day-to-day activities of a person, how fluids are influencing, because engineering is nothing but what we contribute to the day-to-day activities as a common man, how things are getting is, right? So that's what this video, it was very impressive. So I thought of show it before every session of mine to know about the fluids importance in an day-to-day life. Okay. So, okay, our topic is on CFD. So, some people, by funny, they say colorful fluid dynamics because we use mostly the representation of the different parameters what we solve in the computers. So, to just know a predominant specific introduction, we can say something definition. So, CFD is a science that, with the help of digital computers, produces quantitative predictions. Okay, so you need to know the quantitative predictions component, particularly for a fluid flow. So based on the conservation laws, because when you see this particular, just take a pointer now. So this why I put this particular thing is, so it's something like you create a video camera which captures the nature. That is what generally CFD does. So it's numerically we just do that thing. So we just start the thing by designing the video camera which covers what all the nature does. Okay, it may be aircraft flow or combustion flow, whatever the things. Okay, so conservations we'll discuss about detail, because you cannot violate nature. Okay, so because you're going to capture the nature, you need to go along with the nature. So obviously you need to follow the conservation of laws. Okay, so that will get into the thing. So wherever fluid is there, so we can do whatever the fluid modeling using CFD. So that is what I am going to explain in the further slides. Okay. So I said how it predicts things. So CFD provides a quantitative. Okay. So for example, sometimes qualitative, but mainly on the quantitative prediction of the fluid flows. By main thing is mathematical modeling, because the mathematical modeling involves the PDE. You might have known engineering and science people are the participants. So partial differential equation is one of the main controlling thing. More than one parameter if you need to control, you need to have PDE influence, right? So okay, so once there is a more than one number of parameter, you need to solve using numerical methods. So the numerical methods helps where you discretize a domain. Okay, I used to tell to my students the discretization starts where the people started discretizing lands. Okay, if you have a different acres of land, you need to concentrate each and every acre. If you give different kind of you can see some may have rice, some may have wheat, different kind of things like that. Okay, so software tool, it's something like the software tool is a communication between the computer and human, because you are going to give it to the system what you are so going to solve, right? So generally CFD enables a community of scientists and engineers to perform the numerical experiments. What you does laboratory fluid experiment that you try to carry out in the numerical part. That is what we say. It's something called virtual flow laboratory. You can see some of the examples how the real experiment and CFD simulation captures the turbulence content, because turbulence is very important criteria as a fluid engineer you can get into. Okay. Okay, I said you are going to create a video camera. This point you keep in mind wherever you try to solve with the fluid using computer applications. So generally the 3 dimensions it's there as per the regular principle of CFD. So pure experiment, pure theory and CFD. Okay, so when you take fluid dynamics, you might have studied some fluid dynamics or fluid mechanics course in your curriculum. So that is where you start your fluid analysis. When the pure theory comes, obviously you need to know how it works in the laboratory, right? So pure experiment. Okay, so also the 3rd dimension, what we predominantly see in nowadays in the design and the other engineering fields, the CFD. Okay, so whatever, but you should keep it in mind that the CFD is not standalone. If you go with CFD, you have to validate with either theory or experiment, because it's created by you by giving so many assumptions, because when you start modeling, fluid modeling, so obviously you start with some assumptions, right? So whether you use Euler equation or Navier-Stokes equation, it starts with assumptions. Later, after fluid modeling, you get into the mathematical analysis, that is numerical methods. Obviously, it has round of values, all those things. Okay, that is in detail CFD. That is not the agenda of this today's session. Okay, so I like to highlight in from this slide, the CFD is the third dimension of a fluid analysis. Okay, so you like to know about what is the third dimension in detail. That is our agenda today. Okay. Okay. So if it is a third dimension, so you need to know about what is the difference between the second dimension and the third dimension, right? So what experiment does, what CFD does. So obviously you will come to know how CFD influences most of the design process. Okay, extremes we can say. So here we get quantitative description of flow of one quantity at a time. Okay, so if you measure something in your fluid mechanics laboratory or aerodynamics laboratory, you might be known. Here the quantitative prediction of a flow phenomena using measurements phenomena using CFD software. For example, you solve number of parameters which is in the governing equation, which we will see in the further slides. So particularly experiment has limitations, like it is a limited number of points where you have the measuring instrument, those area only you can get the data. But here, so for all the given quantities where you solve, okay, so that I said wherever the quantities are solved, okay, there we can get the data. So for laboratory because you cannot have a full aircraft wind tunnel, because globally it's very rare 1:1 wind tunnel model. So you studied scaling principle, all those things. Here with high resolution, we can have actual flow domain. So if you have a very capable high performance computing, we can have one aircraft into the computing system and solve all the conditions you give and conditions you like to watch. For a limited range of problems, operating conditions obvious, because so there is a wind tunnel high speed wind tunnels. You need entirely. So but here video play same laptop I can do upload பண்றதுக்கு நான் அந்த அவர் பேசுறதெல்லாம் எடுத்து பாப்பேன்ல அதெல்லாம் ரெக்கார்ட் ஆகும்ல there is a main strength you can say நான் கண்டென்ட் ரெடி பண்ணி வச்சிருக்கேன்ல பேசுறதுக்கு CFD. Okay, அத பாப்பேன் YouTube அவங்க क्वेश्चंस கேட்டனால இல்லையான்னு பாப்பேன் because அப்புறம் எப்படி நான் இது பண்ண முடியும் right? So obviously you can go with CFD simulations, you know about the process and things, but the assumptions and the modeling what you do has to be very very fine and accurate, then only you can get the results. Okay, இப்ப நான் கிட்ட சொல்லவா அப்படி some of the error sources of the experiments are measurement errors, some of the flow disturbance. இவங்க கட்டாயத்துன்னு சொன்னாங்கனா மீட்டிங் லிங்க் அனுப்பி விடணும், நான் வர வழி இல்ல. மீட்டிங் இப்போ கட் ஆயிட்டு என்ன உன கட் ஆயிட்டா இங்க மேல சவுண்ட் பேசல யூ லாஸ்ட் நெட்வொர்க் வருது வாட்ஸ்அப்ல அப்ப கட் ஆகும் here and other kind of errors. Phone implementation. These stages has the error, but the very perfect engineer, the job is to minimize that error. Okay, when you try to validate with your experiments, you have validation. So comparatively less error you can see. Okay. So this is the comparison between the second dimension and third dimension, I can say. So when you come to the process, okay. So most of the people I see nowadays, the young engineers, they just do in a computing code, whatever they use, just input the parameter and get some color pictures, and they just give for the presentation or publish somewhere, but which is not good, right? So because if you are doing something to the society or the community, you should be fundamentally strong. That's what I strongly feel as an academician. So if you are fundamentally strong, you should know the process. Okay, so you should be strong about the process first. When you start a process of a CFD, it has three main streams. Okay, first is a pre-processor. Okay, pre-processor is nothing but when you do experiments, you make things ready, right? So you just make everything set up, and before you start the experiments, you need to go good ambience, all those things. The similar way, pre-processor does the setup of everything, and what are the operating conditions you like to see as per your computing power, how much capacity of the grids you need to solve, all those things, the convergence criteria, all other things you will put it in the preprocessor. When you ask any CFD person, people used to say a good pre-processing stage will obviously get into good results. Okay, so the pre-processing, something around 70 to 80% of a particular CFD process, which you do in a very careful manner, obviously the further results are better and validation can be good. So next is a solver. So here the computer is influencing person, or the HPC, or the computing facility what we have as the influencing area, because you'll be obviously having a code, whether you use open form or you use commercial codes. Obviously the solver has to be solved by a computer using a code. The code is a connection between a human and a computer. You can say something like that. Then the processor, I said, right, some of the results, it gives n number of results, hundreds of plots, all those things. But the post-processing is real engineering, I can say. You need to infer the results, okay? What computer gives, generally, as a funny thing, people used to say, CFD garbage in, garbage out. When you give something, it will give something, okay? So as an engineer or a science person, you need to know what it gives, okay? Then only you can just correlate your results, what is your expectation. This is the process of CFD. In detail about the process, you can try to say, this is what I said. So geometry, physics, mesh. So you might have just come to some understanding that if I say pre-processor, okay, these say 3 area, it is the pre-processing stage. Okay, so you need to define a model, you need to just get into the fluid modeling, what are all the flow parameters, discuss, investigate, whatever thing. Particularly if you have a modeling, okay, so the fluid domain, for example, you need to discretize it, I said, right? So now also there are meshless processes are there, but classically we follow the structured or unstructured grid process, that is a meshing. This fellow, if you are very confident about your pre-processing stage, you don't need to worry about the results, because obviously better computing power solves and gives the better results. Okay, so to solve things, you can have steady, unsteady, other convergence criteria. I told the precisions, how singular, double, numerical schemes you can select, numerical methods people you know better, right? So the report, okay, whenever the system is solving, you cannot just wait for the end results and check the inferences. So obviously you just keep trying in between, and just you are ensuring that the things are going good. So it's going as per the validation thing, or as per my expectation, or some experience will give you some clarity of the inferences. Okay, obviously after that post-processing is nothing like, so you just make sure that whatever the things you solve, okay, so residuals we say, from that you take whatever you want, okay, streamlines, contours, vectors, etc. Okay, so I used to tell to our students, whenever you say something, there should be physics behind that, right? So it should be governed by something. So without governing something in engineering or science, we cannot accept it. You just say black theory when he said, believe the initial stage, but the equation derived and proven, which we okay, then only people started listening to him and things. The same applicable to anywhere in science and engineering. You cannot blah blah simply talking. You need to get into an equation form. Okay? Then mathematical and physics and engineering will club together and get into a better outcome, I can say. Okay, fundamentally fluid modeling has to be done. If you say any kind of fluid domain you have, any kind of fluid domain, I don't restrict to air or road. So obviously you need to have I said, right, you need to design a high precision video camera. Okay, so obviously you need to have the 3 main principles, starting with the continuity equation. Okay, so continuity, momentum and the energy. So when you try to observe these laws of the nature, obviously we follow the fluid principles, okay, without violating the law. Okay, that is the main thing. You should keep it in mind, young engineers. So before you start any CFD process, okay, I said, right, the equations should speak physics, because that is a fundamental. So fundamentally, if you are strong, you can solve anything what you get into in your small computing system. Okay. Okay, so these statements, what I said, the continuity, momentum, energy, it has principles, right? So obviously the principle has to govern, then the principle will result into a governing equation, we say. Because the governing equation is backbone of any CFD simulations, because that what it solves is very important. Okay, to start with continuity, the connection is mass conservation, because mass conservation people might have studied, because obviously you need to conserve a particular fluid domain. If you take it, the conservation of mass is very, very essential, right? So the mass conservation, next to the momentum. So momentum will get into the Newton's second law. It's even school students are better in this F equal to ma, which governs the momentum principle. Obviously, energy conservation, which energy is conserved, is a basic principle of the thing, because you will not solve alone fluid and other kind of forces, right? So you need to get into the thermal. Okay, when we say aeronautical high-speed flows as the shocks and thermal influence, right? So obviously the energy equation as a main parameter which solves heat components. In the previous flow chart, if you say heat on off will be done using energy. Okay, this drives by first law of thermodynamics. Because I used to tell my student, because code is a code, because you use any code for using the thing.
அது ஃபர்ஸ்ட்ல இருக்குது, அதுல இருக்கு. அது எப்படி கட்டா யூடியூப்ல கூட கிடக்குங்களா? அது கூட
கடக்கோ நீ வந்து எடுத்து மேட்ச் பண்ணிப்பியா? நான் அப்படியே வச்சுக்கிறேன். நான் என்னோட வீடியோ ஆன் பண்ணாதான பிரச்சனை. பண்ணாம இத பார்த்தே இப்படியே கேட்டு முடிச்சிட்டு இந்த வாட்டர் தேங்க்ஸ் சொல்லி.
Okay, I said when you have a particular control volume, for example, I have a bottle of water, so I'm just splashing it. So I just ask you to model that thing. Okay, first thing what you have to do is you need to know the volume of the bottle. So in the volume, how much water flow is that is the volume you try to model it, right? Fluid modeling, that is the first thing. Next is a grid. So how many number of, because the main advantage of thing is it has a molecule level. So you don't know how many molecules it does in the fluid particular volume what you ask. So obviously what you need to know, so you need to know which point I need to measure the parameters. In the experiments, you know, there are 5 numbers. You just put your petard probe or the whatever the things you want to measure and get the things done. Okay, strain gauge or something. Here the grid is a fellow. Okay, I said in the starting of my thing, particularly the people started discretizing the land, right? So I have some 1 acre or 2 acre land. So if I put different kind of plants in that, I cannot say the same concentration to the all the particular lands. Okay, so I like to have one domain different kind of things, the other domain different kind of things. That is the job. It is done by grids. Okay, when the grids are there, so you need to know about the what kind of discretization process it need to know. So obviously you just get along with the process. Okay, so the grid, how it helps. Okay, so it gives cells or elements. Am I audible, Ms. Suganti?
Yeah, yes sir.
Yes. Okay. Yeah. Okay. So okay, just to confirm, no, nothing else. Okay, so it just designate the cells or elements. Like I said, when you just think about the land, how they discretize as a farmer, so you know better. That's a simple principle. From there we can start. So obviously you need to discretize your volume, the domain. Okay, you need to discretize your particular geometry. Okay, because you need to show the computer, hey, where my fellow is at. You need to solve around that. Okay, so particularly when it comes closer to the geometry, there are the zones you need to mention, also the boundaries. Okay, so for example, when I try to say a particular aerofoil problem or aircraft problem, the same problem can be solved in n number of ways by using a boundary conditions. The boundary condition influence is like that. So maybe we'll see in the detail when we see through the case studies. Okay, how the grids are helping. Okay, so the grids are helping how the convergence can be. Okay, whether even lack of convergence or the rate of convergence, you can just control using a grids. Okay, the better grid, that is a pre-process stage, you need to keep it in mind. So better convergence will be controlled by a better grid. Okay, so obviously when this come to the grid area, I like to highlight some of the points for the young engineers and people. So you need to know about a better grid, because you can say, I just set this bottle, so this bottle can be solved in a 10 points. Okay, maybe lakh points, maybe million points. Okay, so it depends on that. Okay, you need to finalize that which grid system or grid points is giving a better results. That's what we say grid independent system. Okay, yeah, result should not vary with the grid. Okay, so for example, I have 1 lakh, 2 lakh, 3 lakh. So maybe you just compare it, 2 and 3 lakh may be giving same results. Why unnecessarily you waste your computing power? Okay, so you give with the 2 lakh elements for your solving. That is the thing. So obviously solution accuracy, I mentioned that So you need to validate your thing because the CFD is something made from the assumptions, right? The CPU time required, I said, for your computing power, for your convergence things, what kind of grid count is enough and better you need to finalize it, okay? Okay, how I can discretize? Okay, so I cannot randomly test, right? So there is an organized way of thing in the discretization process. So these are all the most shapes we follow for the discretization. 2D, the tri-element we use, and 3D tetra element, it's unstructured element. There are unstructured way, structured way. Only problem with unstructured way is the quality has to be very stringent. So then only you can just follow some criteria and get along with it. Okay. So some of the examples where the meshes, the shapes what I shown in the previous slide are employed. So some of the organized way of thing. So here you can see the grid system which has the quadrant hex mesh combined thing as an automobile analysis. So you can see hybrid mesh. Okay, so you see that this is an unstructured grid here. It's a structure here. So it's a combination. Finally, so as a summation, you need to have a grid point value at each thing where I said, right, the governing equations are solved, the residuals are plotted. So that is your parameter. Okay, finally, when you just post processing it, those residuals will help you converge results, we say, right? Okay, so that is a thing. Okay, so this is the process. Hope some people are clear. Maybe at the Q&A sessions, if you have any queries, we can just solve it, no worries. But you should be fundamentally know about this process because this helps a lot. Because once you are strong in principles and fluid modeling and discretization and the process what you follow, obviously you can confident about your results. Okay, some of the importance you can see. I said, right, wherever fluid is there, obviously I can just work on it, okay, as a CFD engineer. So the architects to design comfortable, because some of the area you know, right, so there will be different kind of natural calamities are happening in different part of the world. So you cannot just have a very blunt design of the building. Obviously you have a better design. Also nowadays the designers of vehicles, the drag reduction gives more fuel consumption, better fuel consumption. People follow these things. Obviously chemical engineers, I said, so you cannot just go and do chemical experiments which is hazardous. You do those things in the fluid modeling. So petroleum engineers, because if there will be long petroleum lines, so obviously they try to get the oil recovery strategies using numerical simulation. One of the human influence thing is surgeons, so they do computational fluid hemodynamics, where the arterial things, the arterial diseases, for example, heart flow, all those things are the modeling, which is a very trending area of CFD. Also meteorologists, you might have seen during the storm, all those area in the news, so they show the particular green, red and images, right? Those are all from CFD engineers, the meteorologists to forecast the weathers and things. So it's a huge computing involved in that, so you need to keep it in mind. Also safety experts to reduce the health risks and the radiation things which cannot be actually captured in the experiments, you can do in CFD. Also military organizations to develop weapons. If you observe my first slide, so the dropping of a missile can be done in simulation and see the safe parameters before you get into the real testing. Okay, so these are all the uses, you can just note it down. Okay, so I said you cannot go 100% with CFD. Okay, I used to just tell my students, when you say 100% matching with the validation, obviously you are manipulating things. Okay, you should keep it in mind. You should not be more smart or over smart for this. So obviously you need to know, because you are a video, you are just designing a video camera which captures reality, what it's happening. Okay, so obviously you should know, so that camera captures the thing. Here the modeling that you try to use it, right, it has some assumptions. Then the next stage is discretization. It's like a zoom in the camera. Okay, 10x, 15x, 20x zooms, right? So that is how the frames you are trying to do. So how much grid you try to match it. Okay, discretization process. So everything has some of the limitation and assumptions. So obviously people cannot accept with CFD alone. So obviously how CFD helped in the sense, previously people used to do 100 experiments Okay, now they are doing 10 experiments as a base cases. The remaining 90 things they are doing it in the numerical part. That is how CFD influence the whole design cycle of anything. Okay, even aircraft or any engineering components, it's influencing. So you should validate your results. That is very important. So compare the results with available experimental data. So that's where you try to fine tune your CFD skills. Perform sensitivity analysis and parametric study. So that is also very important, because uncertainty things should be reduced so that you just believe the results. Okay, so validation and verification to ensure that whatever the fluid modeling you does, it's correct. Whatever the discretization is suitable, so that is a better result for a particular application what you have used. Hope I am clear for this session, because this is the base you can say for this particular session. After this we'll get into some of the applications, because I thought it's whole engineering and science people mixed in it, so some of the industries also they are part of it. So I take some of the 3 case studies, what are the discussion we did in the previous slides, like preprocessor, solver, post processing, how it is employed, right? So then only you can just use it for your applications in future. So some of the codes available, it's not limited, whatever just in my mind I just given here. So these are all you can see which is there a GA based thing. Now people started exploring OpenFOAM because the researchers are very much interested in OpenFOAM. SC2 code also, one of the Stanford University code, is very influencing code for the applications, acoustic studies, etc. So some of the applications like just the missile dropping thing, then I said the vehicle aerodynamics part, and how the ship formation, underwater vehicle, like Ms. Suganthi said, what you can say is RLV, or reusable launch vehicle, or what launching system you use, you can just do it in this fellow. I said, right, the natural calamities or something. This is something like how the industry pollution is happening. It has been modeled. We can see how much enormous computing involved in this. So these kind of image, if you recall, during the storm or something in the news, this is the same thing you can see. This is where CFD employs. Okay, you can just keep, if you are a CFD engineer, you can just probably say, I also work in this area. Hope I am clear about the fundamentals and the principles what we follow in CFD, but also the process what CFD has. Okay, we'll just get into the case study. Okay, so how I just planned in this, one of the main thing is close to my heart is my research work which I did for my PhD. So to start with, that is an external flow problem. Then we get into the internal flow problem. Then combined flow. Okay, this is how I planned the case studies. So external flow problem is something you can say, I just have this hand, flow goes around it, right? It's an external flow problem. I just have my hand like this, flow goes through this or something like this. This is the internal flow problem. So this is the basic things that science people they can just understand in this way. So this is my this is research thing. So particularly turboprop aircraft, you might have seen in several regional aircrafts, turboprop aircraft. In this, the aircraft what I worked, because previously I was in NAL, so where I worked with a pusher type turboprop aircraft. So pusher type turboprop aircraft has some oil cooling problem, okay, during different operating conditions. So we try to solve that. So CFD helped a lot to get into that solving system. Okay. So what is the main thing is, before you get into, you just see this image. So this is the main aircraft which is close to my heart. So this is a SARAS aircraft. Now we say light transport aircraft. It's from India. Okay, we made it from India. So this is a pusher configure, which is very rarely you might have seen, because the pusher kind of things, nothing. There are two kind of configuration in aircraft. One is puller, another one is pusher. Puller, you might have seen the propeller here or engine here, which try to pull and go forward. So here the fellow propeller sitting at the back, it pushes the flow back. So obviously we get the forward motion. That is a basic concept. So what difficulty we faced in this thing is the oil cooler which is placed. This is the nacelle. So there during different kind of idle condition, the cooling is not happening. Okay, so the oil temperatures get shoot up. Okay, so we try to solve using it. What we have done is this is a fan, right, propeller. So we try to, the fan is rotating like this, so we try to use the flow suction of the fan through the oil cooler so that it gets effective cooling. That's the basic concept. So we did experiments on aircraft, in the particular aircraft, and measured what all the flow, because I said, right, I cannot go along with CFD, I need to validate the experiments, right. So I did the experiments on the aircraft, so then got the mass flow rate values at the different locations. The same was validated with the CFD. Okay, so CFD we did for different combinations of the propeller. Mainly this we did with the uninstalled propeller, you can say. Only the propeller was rotating at different RPM and try to match with the experimental data. So that is what we say. So the same thing, it's explained that because both experimental and CFD studies of a typical NASA system, we've done this project. This work has been done in two-pronged, and one is experimental investigation, another is a CFD to mainly estimate the thrust loss. Okay, if you have that fellow in front of a propeller, the propeller is rotating. So if you disturb that fellow flow system, obviously thrust loss will be there. Whether within that limit the thrust loss is there or not, that is what we tested in the experiment. When you see it is a rotating domain problem, so obviously there will be two domains. Okay, this is a static domain, this is a rotating domain. Zoom version, you can see it here, the propeller thing. So this is a, so obviously how the propeller is rotating, that has to be defined by us, different RPM. Like previously, see, one of the main advantage in CFD is you can do sector-wise simulation. Okay, you see this fellow, right? It's like a 360 degree cake. You say a cake you cut in one piece, right, as a sector. So it's a 360 degree domain. So if you like to solve 5 propeller is mine. So 360 by 5, 72 degree sector. I solved the initial thing to gain more confident on the boundary conditions and other operating conditions, nothing else. Then the 5 blade. Okay, these are all the elements and node I said. So when you try to just visualize the elements, okay, the elements, if you have a triangle elements, it has a 3 nodes, right? So the obviously that is how we try to solve the node. So node will have a element to element connectivity. There will be lack elements in the sense the connectivity as center nodes are the thing you need to compare. Okay, so before that I just the prism layers, what you say near, because this is an object. Okay, so near wall generally you should be very careful because that is where all the things happen. So you need to capture in a better way. We generally follow prism layer things because for getting y plus, you say near wall treatment, if you does better y plus value if you want to achieve, so you need to capture the near wall area better. Okay, generally we calculate the boundary layer. Boundary layer is calculated delta, you know, obviously with related to the Reynolds number. For the particular operating conditions, what kind of Reynolds number I have, using the Reynolds number you calculate the boundary line thickness. Depends on the thickness you give the number of prism layers. That is a principle we follow for any simulations. Okay, I said boundary conditions in my principle and process slide. So the same particular problem can be solved in 1000 ways. That is controlled by boundary conditions. Okay, generally I said, right, it is in the solver is solved in the computing system. So you need to properly define what it's supposed to solve, what are the conditions it has to take. Okay, so for this problem we take velocity inlet and pressure outlet. Obviously the far field, what you say, the rotation, the circular domain, the pressure opening. So there are two things you should remember, because the blade and hub. So the blade is rotating in a particular RPM, which just slip the flow. So obviously it produces more thrust. The hub is a holding part of the propeller. So what we have decided is, from the literature you can to know, the blade will be a wall, no slip and free slip. Generally wall has two boundary conditions. So theoretically if you want to understand, nothing but the inviscid and viscous. Okay, when you have a viscous flow, obviously there will be formation of boundary layer. So the flow has to go, the firstmost layer of flow has to stick to the base. Then it keeps a forming boundary layer. It comes to the free state. Okay, that is the no slip boundary condition. When there is nothing, when there is no viscous or inviscid, so it just goes whatever the way it wants. That is the thing. Also the domain interfaces, you have to be in a better understanding, because the propeller is a rotation domain. There will be a bigger static domain. So both has to be properly connected, right? That interface was given by frozen rotor, because for this I have used CFX code, because CFX code was very strong in rotating domain and the turbo machinery issues. Okay, so rotational domain I said we gave different kind of RPMs. Also I said the oil cooler in front of propeller, how much thrust it is reducing. That is the research intention, right? So obviously this oil cooler was modeled using an oil cooler law, which is a opening boundary condition. So it simulates when the flow comes, it realizes there is an oil cooler. That is what we try to model here. So we followed 10 to the power minus 6 to 8 conversion. This is where numerical methods influences what are all the schemes you choose. Okay. Also the turbulence model. So the turbulence model is a very separate area, because it's a, we can say, little higher level of courses. This turbulence model selection is very important to capture, because obviously if there is a ball, the flow is coming, it creates turbulence. Okay, you need to capture, because the turbulence challenge is there are large eddies, small eddies, medium eddies, everything you need to model it and solve it. So that is where turbulence model influences. Maybe in the future we can get separate turbulence modeling course. Okay, once I get into the solving, okay, you can see that how it works, the streamlines around the propeller. So I said, right, there is a oil cooler, propeller, and goes downstream. So it realizes that our rotational domain and how it goes. Some of the upstream and downstream data, we can see how it's getting done. It's a velocity contour. You can see the influence of the oil cooler here. Okay. So this is something like when you try to solve it, you just observe the residuals, right? So you just observe the residuals. Here we did continued momentum, because there is no much thermal involvement, so we didn't consider the energy component. So you can see that. So when the oil cooler is there, the plate 5 thrust is shifting, because that is influencing more. So how much thrust loss we got, that is our thing. You can see some of the comparison. So I said, right, you need to validate your fellow. So propeller thrust, what OEM given is 895.2 kg for this particular operating conditions. So without oil cooler is this, with oil cooler, both the things we have done as simulations. So we could arrive 1.21% the thrust loss because of this fellow we are placing in front of the propeller. So this we discussed with the scientist, and arrive below 5% is the nominal range, which generally they accept when you have installed component. Uninstalled to installed is very much important, because that is where drag component, obviously there is SFC, specific fuel consumption, will come to the picture. This is one of the main case study I like to present. Maybe another 12 minutes I have, right? Mr. Kanti?
Yeah, it's okay, sir. I will continue.
Yes, sir. Yeah. To continue with the second case study, previously it is a propeller analysis. So propeller is an external flow. So this is something like a blade. The flow goes on and here and there. So it creates a thrust. Next we get into the this from KCRI we have done research project for a defense project. So we have done performance analysis of the settling chamber, which is a main component of a trisonic wind tunnel. So any high speed tunnel you can see the settling chamber, even tunnel, but the settling chamber of trisonic wind tunnel has a significance. So that is where we worked on it. So in this project the aim was there different components will be there in settling chamber. So when flow goes through different levels, the turbulence intensity should be kept in level. Okay, so there is a condition need to be followed. So the non-uniformity level also we need to see the turbulence intensity and the pressure fluctuations. So this mainly we did in the CFD role, because it's a bigger component. So you can see, you will get some idea. So this is the main thing, 6395 mm as a component length. So when flow comes from the PRV, it goes through this. So there will be a spreader, different kind of you can say perforated plates. Then there will be honeycomb. All those things will be there. Then the flow goes through the test card. Okay. So this is a general thing. So we have done grid part very carefully. KCRI team involved in the grid generation. So this is a conical spreader. You can see perforated plate, two plates are there. So when it comes to the grid, you can see the meshed model. You can see very dark region in this area, right? Like I said, whenever there is a very minute object, you need to capture better results, you go with a more finer grid. Okay, so that is what it signifies. Okay, so here there will be a spreader, perforated plate 1, 2. So you can see very fine grids also with prism layers which capture the flow in a better way. So this is how we did with a better quality also we maintained. Okay, you can see very closely, okay, how the conical spreader and perforated plate 1. Also I told, right, prism layers we did, and the accepted volume skewness we followed this point 1. So it's a very huge computing thing. This is the element and nodes what we followed our system. The Y plus we used a K epsilon realizable model, so we followed this 8 prism layer we followed. Okay, so that is how we did the pre-processing stage. This is the grid generation. Once the grid generation done, we give the boundary condition accordingly as per the input thing and the output. Obviously, the different perforated plate. What we started is we just did the empty simulation, then we keep added the component perforated plate and the conical spreader like that. So you can just see how the variation along with throughout the settling chamber. So this is on the pressure plot. Generally, when you try to do some kind of simulation as a young people, you have to compare the basic parameter first, the velocity or pressure, how it behaves. So that inference will give you more clarity, so that the next level of data can be taken from that base. Okay. So these are all the velocity plots and the turbulence intensity of the different thing. You can see how the perforated plate, because obviously high speed flow comes from here, so it just expands, right? So you have to control that flow by using different kind of components. So different turbulence thing. The whole I said one advantage here is the symmetry. Okay, you can do the symmetry analysis, then you can just take the full thing. So you can see full model in a particular Y plane, Y view, that is exit plane. So this is a conical spreader which is having a file shape. So perforated plate 1, 2, then it goes to the exit. So along with streamline, maybe streamline will give more clarity on it, because how the flow separation happens, how the flow gets settled down. After this, there will be a you can say mesh, which regulates honeycomb and mesh, so which regulates the flow. Okay, so streamlines in the full pattern you can see. So comparison of the streamline, it has been given in different components. So this internal flow, now you might have got some clarity how flow goes, because the main plus in the internal flow is you have a very prescribed boundary. Okay, you know the volume where it is. For example, this bottle is boundary. Inside that only the flow will be there. If it is external flow, the computing things should be little higher, because you don't know defined volume. So we need to do, previously we used to do domain independent study. Nowadays we try to have a thumb rule and follow the domain finalizing things. Okay. So the final case study which we did for DRDO again, it is a combined. We did in external as well as internal flow. So mainly on the EIV flow things. This we did in 3 phases. One is external flow study on a propeller, wing and nozzle. Before we start, we did one empty propeller, that is uninstalled propeller, to know basic propeller characteristics, then validated with the propeller chart given by the customer. So then we added wing and nozzle. Okay, so the whole system, the external flow we did. Then internal flow through ducts. Okay, the nozzle system has a ducts, right? So how the flow gets into it, those things we did in the thing. Then both internal and external. The main agenda of this particular project is to know the installation losses. Okay, installation losses is nothing but, see, you know propeller. So propeller separate, it's different. When the propeller is installed on the air cap, it disturbs the whole flow spectrum, right? So how it is getting disturbed is the main intention of this project. So you can see this is the propeller we used for this simulation. So the UAV what they used for the analysis. So propeller alone, that is standalone propeller, and along with the aircraft, those things we have done. So this, you can recall my case study 1, similar to that. So there will be a rotational domain and a static domain. So the rotational domain, there are 2 ways from the literature we can choose, or you can do the domain independent study. So how to fix that particular rotational domain. So you can see the values, how we fix for the rotational and static domain. By iterations, we can keep doing it. So validation is the main what you can say is word CFD engineer keep it in mind. So you need to validate with the thing. So we just standalone propeller validation done with the OEM reference things. So generally the value validation should be a better percentage. That is what we follow. So this is also very huge mesh system we followed, because the propeller stream which so with prism layers obviously, so we follow different kind of blade settings. The boundary conditions aspect, thermal influence higher, we get into the density. Because before that we did the critical study and arrived this value. So Simplex is the code which we followed for this simulations. So like I said, CFD has a symmetry advantage. So we just followed symmetry aircraft simulations after the standalone propeller we have done. So that is how we followed. So this we aircraft simulations. So again, pressure based, the same set of things we followed. So install propeller in the sense, you might have seen previously propeller alone the first stage and the aircraft alone the second stage. You need to combine, right? That is the actual thing. In reality, the propeller is installed on the aircraft. So when it is installed on the aircraft, how it is getting results. Okay, so the flow what gets the propeller, it disturbs the whole spectrum of the aircraft, right? So that is the main intention here. So to know that, you need to keep it in mind, uninstalled and install, how the installation loss is happening. Okay, so again it's on the aircraft side. We just very carefully we just modeled and discretized the thing. So you need to show the boundary to the thing. Also the K omega SST is a proven turbulence model for this case. So mesh type polymesh we used the same Simplex we followed the simulations. Okay, so when it comes to the installation losses, so you need to know how the flow disturbance happening. So after the propeller, how the inflow of things happen inside the nozzle. Okay, so that is where you can see the wake region, the different operating conditions we have done. So on the geometry side for the third combine we have done, and our team worked day and night and arrived at different kind of approaches. Okay, porous media approach for these kind of simulations, we with a better mesh count and quality we could achieve this. So you can see how the things are happening. So we can see intercooler, one of the main thing. So where you can see that, so how the flow is getting in using a porous media approach we solve this simulation. Also radiator. Okay, radiator meshing, you can see very fine grids we try to get it, because the cooling airflow domain we need to model it properly. Okay, so the radiator meshing, because radiator is nothing but an oil cooler in the first case I explained. So it has a staking of different fins, we very fine fins we model, and the whole engine heat load calculations we done for different kind of conditions. So the heat load calculations also we got from the fuel consumption curve. So we arrived those things. We can see the velocity contours in the fluid domain what we created. Okay, so external part, when you try to achieve, you try to have a both comparison along with the propeller, the aircraft and the radiator and intercooler components. So you can see the meshing, how carefully we carried out in the different things, because preprocessor is very important. Young engineers should be very careful in the pre-processing stage, because you need to be a very fine on the grid generations. Okay, so temperature contour we can see for the different conditions, flight conditions. So also the velocity contour, the pressure control. So these, because here the thermal loads also influencing, obviously the heat was on. Okay, so the energy equations was also solved. Okay, so some of the results of the intercooler thing for the different operating conditions. Okay, charge air, how much it is there, cooling air, how much it is there. Okay, so I try to cover some of the main areas we generally worked on it. We did several case studies, also the research projects. We still working on some of the DRDO projects and the research solving. So mainly the whole glimpse I like to highlight here. Young engineers should know the fundamental principles in the fluid modeling, also the solver settings, what they do, because whatever they're giving to the computer, they should know, because then only the computer solving whether it's correct or not, they can just revert back, right? The inference is very important. So that is what I like to highlight engineers. I'm just happy to have any questions, Mr. Gandhi. Yeah.
Yeah, so thank you, sir. Thank you for the presentation. I have some questions here.
Yes.
Yeah, okay. The first question, how can CFD be used to optimize the design of hypersonic vehicles, particularly in addressing the issues related to thermal management and shock wave interactions?
See, it's a very good question. Like I said, how you model your fluids, okay? When there is a hypersonic dominant problem, obviously the temperature influence will be there, because you said the question itself. So obviously the energy equations quantity will be there. Because I thought of highlighting this, when we say Euler equation and Navier-Stokes equation, generally we solve in computing most of our current problems full Navier-Stokes equation. Okay, the full Navier-Stokes equation, how it helps in the sense, whatever the residuals you like to solve, obviously you get into that. So those are the things. So every governing equations what you have, those things you can solve it and get the outcome accordingly. Okay, so it's a very possible thing. People are doing it. Okay, hypersonic vehicles. Only how your operating condition works and the governing equations, the fluid modeling what you does. That is important, but we need a high computing system, because you solve n number of variables in your governing equations. It's a full Navier-Stokes equations. Yes, hope I answered
Yeah,
your
okay. Okay, thank you, sir. Sir, what role can CFD play in the development of more efficient propulsion systems such as the scramjets or hybrid rocket engines?
See, when you try to take scramjet and the hybrid rocket engines, see the combustion flow is also very proven in CFD. But the main challenge here is, we say the UDFs generally, user-defined functions, because it's not very ready available things, combustion, because you don't know how things are happening in the whether the hybrid thing or normal scramjet. Okay, so you need to properly define the functions as per the theoretical thing. We try to calculate and influence that in a backend code. In open form, it's more viable. In commercial codes, you need to know the particular code and influence that in the different kind of combustion. But it helps a lot, because the computing system solves how you model it, right? I said so. The experiment facility for those things are very challenging. Okay, but you try to model all those things, and finally you can just have one test and validate your thing. That is how we solve scramjet and other hybrid rocket system things. Thank you.
Okay. So can CFD simulations integrate more comprehensive models of chemical reactions and radiation effects for more accurate predictions of spacecraft re-entry dynamics?
Yes, very much yes.
Okay.
Because recently we attended on the symposium in the
Okay.
defense lab. So we saw those kind of things from because Gaganyaan, you might have seen, which very strongly working from ISRO. Also different kind of space vehicles from our ISRO. See, they worked these re-entry component, because where high temperatures are influencing. So they model that and they try to get the results, but it's a very long process, but it's proven, and people try to get the optimization of the modeling from the re-entry area. Yes.
Okay. Then how can the machine learning algorithms be integrated with CFD to automate and improve the accuracy of simulation processes in aerospace applications?
Yeah, because I expected this question because nowadays people always say machine learning, artificial intelligence, IoT influence in every area. But what I can say as a fundamentally CFD engineer, so those things are data, right? So obviously people play with data for machine learning and IoT things. So when there is a proven system, you have a number of data case studies, you just compare it and develop a particular system. But very new cases, because you don't know fluid how it's behaving in some of the cases, so those areas it's not applicable current situation, but which is proven case. You have a very long set of records for a particular simulation case, you have all the data. So using the data, because we try to work on the particular machine learning and the influence of AI in the CFD, we try to get the data that, because previously we used to say that as optimization schemes, that now it is getting into the machine learning and AI, but it is getting into, but I cannot say it's 100% evolved here, but people are working in the research mode. Those.
Okay, sir. This is my final question. So, what advancements are needed in CFD to better simulate the particulate flows that are encountered in planetary exploration missions, such as a dust interaction or Martian or lunar surfaces?
Yeah, this is a very interesting question because space ambience, because any CFD or aerodynamics, the challenge is how you model your flow. Okay, so the modeling has to be properly done. When you try to model, in the sense, people think that it's geometry. It's not like that. The fluid modeling, what it does. Okay, for example, the areas what you said is the operating conditions need to be known. Okay, some of the cases people started simulating, because mass or some of the operating conditions, if you know, see, two things you should know. So the operating conditions, what it is, you should know how it is converted into equations which is solving those operating conditions, because those parameters what it is there in the operating conditions is to be solved, right? So that is, you solve for 1,000 or lakh iterations, then you get the converged results. So those area you need to know the operating conditions. If your operating conditions are clear, then the governing equations drive the operating conditions. You can just model it, then you can get into the better. But it's research things are going on. People are doing it in the known operating conditions. Yes.
Okay, sir. Thank you, sir. Thank you so much for the answers. So the answers are very useful. I hope the access and the participants can understand about that. So finally, so on behalf of our organization and all the attendees, I extend a heartfelt vote of thanks to Dr. Prem Kumar for his invaluable contributions to today's enlightening session on applications of computational fluid dynamics in the aeronautical and aerospace sector. So Dr. Prem Kumar's profound insights and detailed exposition have greatly enhanced our understanding of the crucial role that CFD plays in the advancing aerospace technology. And Dr. Prem Kumar's deep expertise and his extensive work in both experimental and computational aerodynamics have not only illuminated the complex dynamics of fluid flows in aerospace applications, but also inspired our community of students, educators, and industry professionals. His dedication to applying these sophisticated computational techniques to real-world problems such as the propulsion system, performance, and aircraft design highlights the practical impact of his research. So we are immensely grateful for Dr. Prem Kumar's willingness to share his knowledge and experience with us, his commitment to fostering the educational growth, and his ability to translate the complex concept into understandable terms have left a lasting impression on all of us. So thank you, Dr. Prem Kumar, for your significant contributions to the field of aerospace engineering and for taking the time to guide and inspire the next generation of engineers and researchers. Your presence today has undoubtedly enriched this session and motivate us to pursue the excellence in our respective fields. So thank you, sir. Thank you so much for this session.
Thank you so much for Temstech and Mastering Up for the invitation. Hope the session is useful. If anybody want to know more technically, they can just write to me in this mail ID. Thank you so much for the participants.
Yeah, thank you, sir. Thank you so much.
Bye.
Yeah.